Today I will be presenting briefly on the synthesis and structure of well-defined silica-supported sodium doped tungsten oxide catalyst for oxidative coupling of methane. Oxidative coupling of methane, which converts methane to ethylene, is the only direct conversion method which is not thermodynamically limited. However, owing to kinetic limitations, it requires a catalyst. Manganese-doped sodium tungstate supported on silica is considered the state-of-the-art catalyst for OCM, with around 20 to 25% C2 yields reported. Therefore, the objective of this talk is to generate structure-function relationships for this catalyst. We synthesized a series of model catalysts with varying sodium-tungsten molar ratios, such that only dispersed phase tungsten oxide surface sites are present and no phases are present in the catalyst. Raman analysis shows that as the sodium to tungsten molar ratio increases, the tungsten oxo band moves from 983 to 935, which indicates bond elongation induced by adding higher concentrations of the sodium promoter. Next, we studied the electronic structure of these sodium promoter tungsten oxide catalysts. Once again, we observed strong trends in ligand to metal charge transfer band positions where increasing the sodium content blue shifts this LMCT band from around 250 to 230. Moreover, for all these samples, the edge energy or band gap is high, which indicates that the surface sites are isolated and not polymerized in these catalysts. Knowing the structure and surface properties of the model catalyst, next we conducted methane plus oxygen temperature program surface reaction study to probe the activity and selectivity of these model catalysts. The low ratio catalyst is shown in blue, while the high ratio catalyst is shown in red. TPSR clearly shows that methane conversion starts at around 570 for the high ratio catalyst, while it starts at around 670 for the low ratio catalyst, meaning the high ratio catalyst is more active. However, an analysis of the product shows that the selectivity for the high ratio catalyst is around 58%, while it is around 71% for the low ratio catalyst, where selectivity is defined as the selective yield to total yield ratio. Results clearly show that a fully dispersed phase catalyst with sodium coordinated tungsten oxide sites where sodium tungsten ratio is much less than 2 is significantly more C2 selective, although less active. In summary, we showed that isolated dispersed phase sodium coordinated tungsten oxide surface sites where sodium tungsten ratio is much less than 2 is as active but slightly less active but C2 selective for OCM than the crystalline phase sodium tungstate catalyst traditionally used in OCM literature. Thank you.